We are back and ready to talk about semi-direct products. Almost. There's a little bit more to say. Let's look at another example of a short exact sequence, a very important, famous example. So let's consider the following. So suppose we had in the middle the integers modulo p squared. And we took the map to the integers modulo p, the surjective map, where we take one of these elements, so I'm thinking about writing the elements of this middle group here as choosing representative 0 up to p squared minus 1. And I take the homomorphism where I look at that modulo p. So that's a surjective group homomorphism. And the kernel of this, well, it's mod p, right? So the things that go to 0 are going to be all of the divisors of p, right? Or rather, all the multiples of p. So it's going to be everything of the form np such that, n, we could say as n ranges over the integers, but we're just looking at those. We're just going to be looking at each of those representatives going mod p. So this turns out to be also isomorphic to the group z mod p, right? So if you want like a concrete example, consider, say, 0, 3, 6, right? If you look at these three numbers under addition, modulo 3, this will be isomorphic to the integers mod 3 into z9 into z3, okay? Just to make things more concrete. So in general, this is a short exact sequence. And now the question is, well, does there exist? Well, we're building this whole machinery of exact sequences and building groups out of other stuff. But is there anything other than just taking products? Anyways, it'd be very silly for me to make these videos if it wasn't the case, right? But that's not very good reasoning. We want to be a little more rigorous. So it turns out that in general, if there was nothing other than products, it would have to be the case. It would have to be the case then that zp cross zp is isomorphic to z mod p squared. But this isn't true. This isn't true, right? Why isn't it true? Well, for one, I would suggest, as I've quoted in other videos, consulting the fundamental theorem of finitely generated abelian groups, or just fundamental theorem of finite abelian groups. The other way you can see this is that this group here is cyclic, right? It's generated by the element 1, so it clearly has an element of order 1. Meanwhile, over on this side, the largest order any element can have is p, right? If you take any element, add it to itself over here, p times, you'll get the identity element. So that's an upper bound for the order of elements. Okay, great. So this means the abstract theory we've been learning between the previous video and this one actually means something. There's something else something more complicated going on in these exact sequences than just taking products. Can we do more to try and understand exactly what that is? And does this account? Okay. So in order to better understand the cases that aren't products, it might help us to better understand the cases that are products, and to try and turn some of that into the language of these exact sequences, right? So again, we have this example that I left you with last time for homework about short exact sequences, the short exact sequence given by a product. So what's going on in this case? Well, there's a certain kind of symmetry here, if you'll notice, right? It turns out, for example, G, as we saw, right? The fact that we have injectivity here, or exactness at this part of the sequence, G is isomorphic to a subgroup of the Cartesian product, right? That's something that's going to be true in all of these in all of these exact sequences, right? So if I have any short exact sequence, then most certainly I is going to be an isomorphism onto it, from N onto its image, and that is certainly, well, in fact, I can even just write a subset sign, most certainly a subgroup of G. Right. So in the case where we had, I guess I'll write it as N and Q, let's say. So in the very special case where we had N Cartesian product Q, what was the case there? So we had this isomorphism, right, onto its image where N got sent to N and the identity of Q, right? So it's pretty easy to see that we have this isomorphic copy of N sitting in the Cartesian product given just by all of those elements of this form. But you'll notice that actually in this particular perspective, the same thing happens with Q, right? We have this N times Q is isomorphic to Q times M. Right? So there is this symmetry present here. And so we have an isomorphism between Q, and again, we just do the same thing. We put the identity in the first component, and we just range over all elements of Q in the second component, right? And so, again, what is our sort of convenient language for discussing the relationships between groups? Group homomorphisms, right? It's all about the group homomorphisms. So I can say abstractly, yeah, Q is isomorphic to some particular subgroup of G cross H, but I can do even better, right, than saying, oh, it's abstractly isomorphic. No, I can write a particular homomorphism down from Q into N cross Q, which is exactly analogous to before, right? So how does S act on an element Q? It sends it to En comma Q, right? And notice furthermore, so this is a concept that comes up a lot in mathematics all throughout. Algebra, homotopy theory, geometry. This is a special example of something that's called a section, right? So S is a homomorphism, which also satisfies the following property. So remember, this map was called Q, this map was called I. If I were to apply S to an element Q and then apply pi, it would be the case that, so I would get pi, En Q, and then where does pi send En Q? It sends it to Q, right? So the thing that makes this a section is the fact that S composed with pi happens to be the identity map. Okay, so this is something that's special about the direct product. To what extent does it generalize? What else can we capture? What are some other things, right? So again, we're really talking about this in terms of different morphisms and properties. So let's go back and try and write things a little bit more generally now. So again, we're still going to have N. We're going to have I. We're going to have G in the middle here. We'll have pi, Q. And now we'll suppose that we have a section to our short exact sequence here. Okay. And something else that I want to point out. So thinking about N cross Q, what does it look like when we take a product of elements in N cross Q, right? Because obviously there's something about the actual group law going on here that's important, right? So if I had something like NQ MP, well, I know I can just combine those elements, right? I just write them beside each other like this. So we might try to mimic that with we might try to mimic that with the isomorphic copies, right, of I of N and S of Q inside the group G, right? Maybe better yet, just to help clarify things, so I'll keep things in blue to write this as a separate example. But I think this will be useful to highlight the differences and similarities. So making this a bit more consistent with this notation, what is this saying? It says that I of n, right? So NQ is also can be written as the product N1. So here by 1, I mean the identity of N. I'm going to write 1 here, or sorry, this is the identity of Q. This is the identity of N. I'm just being extra lazy with my notation, right? This is the same as the product of these two elements. And so N comma 1 is I of N. 1 comma Q is S of Q. And I can do the same thing over here, right? So this would be I of M and S of P. And so on the other side of the equation, this would be what? This would be I of N times I of M. Well, of course, perhaps splitting this up, right? This is NM1, QP1, and M1 would be I of NM. I wrote that backwards. This is 1. Here is QP. This would be S of QP. And then I'm using the fact that these are homomorphisms to split this back up here. Okay. So what's going on? What does this tell us? Things are starting to look pretty confusing and complicated. The point is, these two sides of the equation should be equal, right? And notice that they're just rearrangements of each other, right? I'm simply taking the symbols IN, IM, SQ, and SP and just putting them in a different order. Now, this is perfectly valid if the group in question is abelian, right? If this group G that they were being built out of was abelian, no problem, I could easily do it. But that's not the case. What's interesting is this seems to be valid in more general cases, right? Because I said nothing about N and Q being abelian. So if N and Q were abelian, you take their Cartesian product, certainly that resulting group is going to be abelian. If you take N and Q and one of them is not abelian, that resulting product will also be not abelian. So it's kind of interesting that in the product case, we have this rearrangement that is always possible, right? So let's try and take a look at what would happen, right, if we tried to do this in our more general scenario. So I'll switch back to the white marker to now say, okay, I'm imagining this more general scenario. And one of the key things I might try to repeat is this fact that I was able to take an element NQ and split it up as this product, right? So the thing was that it looked like that everything in this group, certainly every element of the group N cross Q could be written in the form, so NQ could be written in the form IN SQ, right? So every element of the Cartesian product I was able to write as a product of elements in the images of my section and my inclusion map. So we could say, well, I'm trying to show that everything's a product. You know, I know it's going to fail. What's the obstruction, though? We're really trying to get into the weeds here and understand what's the obstruction to everything being a product in general. What really went wrong in the case of the integers mod p that prevented this from being a product? What's really going on here? Let's see if we can capture this in some sense. So we're going to ask ourselves, okay, I want to try and write every element of G as I of N and S of Q, right? Seems reasonable. And like above, like in the case of the products, I want to see, well, what happens if I try to multiply two of those elements together, right? NQ times MP. So I'll write out MP in a very similar way. So we get here SP. Okay. And now, so this looks exactly analogous to the left-hand side of my equation. I would really love to be able to say, if it's truly a product, I should be able to rearrange it to get it to look something like this. But again, I'm in this arbitrary group G. I can't really just randomly swap elements willy-nilly and just sort of do whatever I want. What we can do, though, is probably the most famous trick in all of mathematics that you've been using since junior high. And that is like adding by 0 or multiplying by 1, but doing it in a sneaky way. So what we're going to do here is I'm going to take this and I'm going to rewrite it as IN SQ IM SQ inverse SQ SP. So in fact, these two things are equal, right? Because this term here cancels out. So this is perfectly valid. And now here's where I'm being a little bit clever. I am, right? This is by the assumption of exactness on our sequence. This is a normal subgroup, right? So N is supposed to be isomorphic to a normal subgroup, right? Its image is equal to the kernel of pi. This is by assumption. And so therefore, this is in fact an element of N, right? Or rather, it should be an element in the image. So this is some element in the image. So this is I, N, and now I should be able, because this thing is an element of the image, I should be able to write it as I of something, right? So what is that something, though? Well, I guess it's going to be some element of N that depends. So I'm going to write phi. It depends on the Q here, and it depends on the M. So I'm going to use deliberately suggestive notation here. And then I have these remaining pieces, the SQ and SP, right? So if we imagine then, we try to now, so we found something sort of interesting crop up here. And let us go back for a moment and imagine that we were trying to write this in terms of a product, right? So if I was trying to write this in terms of a Cartesian product, what would this look like? Well, IN we are writing as n comma 1. I of this should be phi sub q m comma 1. SQ should be 1 comma q, and SP should be 1 comma p. And now if I were to recombine all of these together, it would be n phi sub q of m comma qp. So it looks very much like a product, but it's sort of twisted by this thing, right? And now what is this q? Well, it's a map. Right? It's a map. And let's think about what's happening back in the group G before we went over to say pretend world. Well, we took this element IM and then we conjugated by something in G, right? So N is a normal subgroup. And I will, right? So N, or rather, let's say I of N, is a normal subgroup. And so, of course, we know that we can conjugate n by elements of itself, right? And those all give us automorphisms of n. Those are called inner automorphisms of n. But we have something interesting that goes on in the case where n sits as a normal subgroup of G. For any element of G, remember that conjugating the image of n here gives me back that group. So, in other words, any element of G conjugation by an element of G actually gives me an automorphism of n. So what's going on here? It's like we're taking the product, right? In this case, it's just like we're taking the product, but what am I doing? I'm applying some sort of automorphism. So whatever phi q should be, it should be an automorphism of I of n, or of the group n. The way I've written it here, it should be an automorphism of the group n. Interesting. So coming back to this situation, right? So if we're trying to mimic the behavior of products, I have this inclusion into G, I have a projection, I have a section. What should happen in this case? Well, really, part of the data I need to construct this group G should be for each choice of Q, I get an automorphism of n. Okay, but let's think about this for a second. There's a way that maybe I could reason it a little more explicitly, but let's cut to the chase. I'm delaying and stalling a lot. Again, what kind of maps do we normally take in group theory? Do I just take a function? I mean, so what is it? I mean, the process, I'm taking Q, and I'm sending it to phi of Q, some automorphism. Now, what do we really tend to care about in group theory? Is it functions from groups to one another? No, it's automorphisms, right? It's automorphisms. So what this really should be is the notion of an automorphism. And so here we come around, and I don't know if this is more confusing for you, but I hope that maybe it makes more sense, the following definition of the semi-direct product of two groups. So given two groups, N and Q, and a homomorphism from phi into, phi from Q into the automorphism group of N, the semi-direct product, N, now we put it the symbol this way to indicate that N is the normal subgroup, and sometimes we get lazy and drop the phi, but if we want to highlight which homomorphism we're choosing in particular, the semi-direct product of N and Q with respect to phi is defined as the collection of all products and Cartesian product, right? So we're running over all pairs, just like we ordinarily do in the Cartesian product, but the difference is the group operation is now different, where what is our group operation? N comma Q multiplied with M comma P is defined exactly as above. So N times the automorphism determined by Q applied to the element M, and then comma Q times P in the second position. So this is exactly what we found up above, right? So, I guess maybe as homework, I will challenge you to prove that n, in fact, in this definition, n always is a normal subgroup. And I would also challenge you, again, this should fit into our picture of short exact sequences. So I would challenge you to write a short exact sequence. What have I done? That should be a Q. Right? Write down the maps that define, I claim that they should be fairly obvious, right? The inclusion of n into here and the projection onto Q that realizes this as a short exact sequence. And prove that it has a section, by the way. Prove that it has some section S. So that is a great exercise to gain some intuition. And remember, this all came out of trying to reapproximate the concept of the direct product of two groups. So conceivably, there should be the product, the direct product, should be a special case of this. And the direct product, I mean, that was sort of the most basic example, right? Where everything worked really nicely. So what might you guess, right? The direct product, according to this definition, should correspond to some choice of homomorphism from Q into the automorphism group. Okay, so even if you weren't trying to rebuild the direct product out of this, you want to search for examples. As a mathematician, you search for the most basic examples first, right? So we need to pick a homomorphism. Oh, what do Q and N look like? I don't know. They're abstract groups. Yeah, there's one homomorphism that's always staring you in the face. The zero homomorphism, right? It's the one that sends everything to the identity. So suppose that phi was the zero homomorphism. What does that look like? So if phi Q is if it's a zero homomorphism, that means for all Q, this is phi Q is the identity automorphism of N. And so if we go up here, what does that say? Well, this is just N, comma, you apply the identity to M, QP. And so what have we recovered? Indeed, the semi-direct product for phi being the zero homomorphism is in fact just the ordinary Cartesian product of these two groups. Okay, so let's try and find a non-trivial example, right? We have a whole class of trivial examples. How can we try and cook up a non-trivial example? Again, we're mathematicians, so we try and think about the most trivial groups that we could cook up first. Zero's not really gonna work. You're just going to end up getting if you take the trivial group, you'll just end up getting the same group back. So that's not really gonna work. What's the next most trivial group? We could try Z mod 2. The thing is, if we choose Z mod 2 in this story to be the normal subgroup, right? Then we need to choose an homomorphism from Q into the automorphism group of Z mod 2. But the automorphism group is trivial, and so as we've seen, we're just going to get the ordinary Cartesian product out of that. Okay, so that doesn't help us find our non-trivial example. What's the next simplest group we could possibly take? For the normal subgroup? The integers mod 3, right? That's the only next possibility. Okay, so what's the simplest non-trivial subgroup I could take or non-trivial group I could take for Q? The integers mod 2. And so finally, this will give us an example. And so what do we need to choose here in this case? Well, I need to take a homomorphism from the integers mod 2 into the automorphism group of the integers mod 3. Well, the integers mod 3, this automorphism group has two elements. One is of course the identity. The other one I'll call phi, which is given, I can just write it out explicitly. So phi, of course, of 0 has to be 0. It just swaps the other two elements, right? So phi of 1 is 2, and phi of 2 is 3. So what is this? So again, we don't want to choose the one that goes to the identity homomorphism. We want to choose the one that goes to phi. And our question is, what is this group? So I'm going to show you the slick kind of cheater's way to argue what the group is, but I would encourage you, once I give you the answer, to come up with your own more explicit homomorphism. I'll talk about an even better hint in a moment. So how do we look at what this is? So here's my slick cheater's way of proving it. I'm going to look at 2, 0, and I'm going to multiply this together with 1, 1. So according to my rule, this should be 2 phi sub 0 applied to 1, and then 1. But remember that I should say sorry, I've done something very silly here, and I apologize. So let me say this should be phi for the non-trivial. Sorry, phi is the map that goes from here. I'm going to call this other one psi for the non-trivial automorphism of Z mod 3. Phi is the map that sends 0 to the identity and sends 1 to psi. Okay, there we go. So phi 0, 1, so this becomes 2 times the identity applied to 1. And mind you, these are abelian groups, so I'm going to write my notation additively. So this becomes 2 plus the identity applied to 1, 0 plus 1. And this is just going to be, 2 plus 1, comma 1, which is going to be equal to 0, comma 1. But now I'm going to look at those elements in the opposite order. What if instead I multiplied 1, 1 with 2, comma 0? Well, my multiplication rule tells me that there should be 1 times, plus additive notation, phi sub 1 applied to 2, comma 1 plus 0. So this is going to be 1 plus, so phi comma 1, that was going to be psi. So this is psi of 2, 1, and psi of 2, remember psi is the non-trivial element, so it maps 2 to 3, or sorry, gosh, I wrote nonsense here. This whole thing has been a mess. I'm not recording. I don't have time for that. Sorry, this should send 1 to 2 and 2 to 1. So psi of 2 is 1, and so this becomes 1 plus 1, comma 1. 1 plus 1 is 2, and so what do we find? These two elements are not equal, right? So what does that mean? That means that 2 comma 0 multiplied by 1 comma 1 is not equal to 1 comma is to flopping the direction. So what does that mean? That means I have a non-abelian group of order 6. There is only one non-abelian group of order 6. Therefore, this must be the semi-direct product. Must be the dihedral group of the circle, or sorry, of the triangle. So D 2 times 3, right? So the dihedral group of the 3-sided polygon, or we could call this S3, the symmetric group on 3 things. So if you want to construct an explicit isomorphism, as I'm giving you for homework, then you should identify a normal subgroup of order 3 of the dihedral group or of the symmetric group, for which I contend there is a quite obvious choice, and let that be your inspiration, and see if you can construct a very explicit isomorphism. Okay, so that is semi-direct products. Hopefully, in a finite amount of time, I will produce more videos in this mini-series diving into extensions of groups and things like that. So I will see you then.